Okay, thanks very much. Thanks very much for this introduction. Can you guys hear me?
Yep. Yes,
Yeah,
yes,
great.
yes.
So, as Gabriel said, the title of my talk is Angular Fractals and Thermal CFT, and I'm very happy to be here virtually. Um, and to the extent that I say anything new, it'll be based off of mostly this paper, which appeared in May earlier this year with Jeha Lee, Shraddha Pal, David Simmons-Duffin, and Ishin Shu. But some of what I say will also be based on a paper from about a year ago with Jeha Lee, Hiroshi Oguri, and David Simmons-Duffin. And also a lot of what I say will be kind of review of older material as well. But these are the references you can kind of take a look at afterwards if you're interested. And let me just start with some very big picture motivation of what we're going to talk about. So I hope everyone in the audience here can agree that conformal field theories are very interesting. And there are many, many reasons why you as a practicing theoretical physicist might be interested in CFTs. Um, you could be interested in well, you could be interested in quantum field theories in general, and CFTs are landmarks in the space of these QFTs because they're invariant under RG flow. So if we don't like to organize quantum field theories by where they moved under renormalization group, and CFTs are landmarks here. You could be interested in critical phenomena, and some second order phase transitions are described by conformal field theories. For example, a point in the phase transition of water is described by the critical 3D Ising model. You could be interested in string theory, and the string world sheet can be described by a two-dimensional conformal field theory, a nonlinear sigma model with some target space. You could be interested also in quantum gravity and anti-de Sitter space, and then via ADS-CFT, you'd be interested in conformal field theories as well. And also, you could be interested in various pure math applications, which conformal field theories can also help answer. And so the question that I want us to have in the back of our minds during this talk is, how do we understand some basic facts and consistency conditions of conformal field theories? In particular, the question I want to ask is, what are universal features that all CFTs share? So let's now forget about the details of any one particular CFT, like 3D Ising model, whatever, and let's just ask, what are some things that all CFTs share in common? Now, in two dimensions, in CFTs in two dimensions, there's a very canonical and beautiful answer, which we learned from Cardy in the 80s, which is that the entropy of a CFT is completely universal at very high energies, or very high scaling dimensions. In particular, from modular invariance of the torus partition function, Cardy showed that the entropy or the density of states of a CFT with conformals with scaling dimension delta and spin j has this universal form where there's one arbitrary parameter, the central charge c. So everything else here, deltas and j's, are just the quantum numbers of the state you're looking at. You have to sufficiently smear them. But once you fix this parameter c, then the entropy is fixed. Of course, c also has interpretations in terms of some stress tensor OPE, and things like this. But for the purposes of this talk, I'm just going to view it as a single real number, which parameterizes some data about the CFT, which parameterizes the entropy of the CFT. And this is valid when delta is very large compared to C. Actually, this more precisely should be the twist is very large compared to C. More precisely, it should say delta minus J is very large compared to C. Um, and this is derived from modular invariance of the one loop of the one loop partition function. More precisely, it means that if I write the partition function as a function of some modular parameter tau, and this is a trace over all the states weighted by their dimension and their spin, this is invariant under some large diffeomorphism of the torus. So this can be written as a path integral over the torus, but the torus has some large diffeomorphism parameterized by the group SL2Z. If you act with this group SL2Z, the one loop partition function has to stay the same. And even more precisely, let's now forget the spin and let's just grade by the temperature. The spinless bootstrap says that roughly speaking, the temperature is invariant under the temperature to 1 over the temperature. This is kind of a generalization of some Kramers-Vannier-like duality. And if I take the limit of beta goes to 0 and take z of beta inverse, this is like taking the very low temperature, right? The low temperature partition function. And the low temperature partition function is given just by the vacuum state. And in two dimensions, the vacuum has a universal Casimir energy given by the central charge. And so if I equate this to the left-hand side and take an inverse Laplace transform, this can read off the high energy density of states. And if you do this very carefully and also keep in track the spin, you get this formula right here. Now, this is valid for all 2D CFTs. Okay, this is valid for the 2D Ising model as well. But for a very special class of CFTs, namely the holographic theories, there's a very beautiful interpretation of this formula in terms of black hole entropy, namely that the log of the density of states, once I change delta and J to the mass and the spin of a BTZ black hole, it exactly matches the area divided by 4G Newton on the nose. So far here, this transformation beta to 1 over beta, this is called the S transformation. This is one of the elements of SL2Z. But of course, we know there are infinitely many elements of SL2Z. And you could ask, can we learn anything from modular invariance from not just the S transformation, but also more complicated elements of SL2Z? And the answer is yes. You'll learn different data that's some more complicated spin-weighted density of states. So for example, suppose you were interested in computing the partition function, but with an insertion of -1 to the j. Okay. So first of all, the left-hand side of this equation, it's the same as without the -1 to the j, but shifting this omega by pi over beta. Right? If I put pi over beta as omega, then I get an e to the I pi j, which is the same as -1 to the j. Right? So you might have asked like, oh, can I compute this left-hand side by just not inserting the -1 to the j and then just inserting omega equals pi over beta plus a small fluctuation? But the answer is no. It turns out that if you want to be able to trust what the value you get from the Cardy formula in the canonical ensemble, you need this omega to be order 1. Otherwise, your saddle point approximation is no longer good when you take the inverse Laplace transform. So I can explain that in more detail if people want. But the upshot is, if you want to know this partition function with this -1 to the j, this is what we call large angular fugacity. You can't just plug in omega to be order 1 over beta because you'll get the wrong answer. And you really need to do a different modular transformation on the vacuum to get this answer. So to get this at very high temperature, you need to do a modular transformation, which is -1, 0, 2, -1. That's the 2x2 matrix you need. And when you do this and you compute this and you do the modular transformation, you find this is the expression at large temperature, so when beta is very, very small, for the partition function with this -1 to the j insertion. So it's exactly the same as the previous answer, but there's no factor of 4 here. Okay, so if there were no -1 to the j here, you would erase this factor of 4 in the denominator. And no, that's different than if you take this answer without -1, without this factor of 4, and set omega to be pi over beta. Right, you'll get the wrong answer then. Does it make sense what I'm saying? Okay. So this now gives us more spin-refined information because it tells us kind of the density of states of even spins minus odd spins. Okay, if you want, you might be familiar with like a Witten index where this is -1 to the f. This is not that. This is -1 to the j. So this is like a square root of -1 to the f, if you like. And for 2D CFTs, this is a universal answer again. It depends on just the same coefficient c, and there's a factor of 1/4 in the exponent. You can play the same game not just with -1 to the j, but with any rational angle, like e to the 2 pi I p over q times j, and you'll get some things. So in 2 dimensions, we can derive all of this from modular invariance. Modular invariance is just an incredibly powerful tool for us to use. But a very reasonable question you could ask is like, do there exist similar formulas like this one right here for CFTs in d bigger than 2? So we don't have modular invariance in d bigger than 2 CFTs, but a lot of the physics should still be the same. So it's very reasonable to ask, do there exist similar formulas? So for example, one place where the physics is the same is I said that for 2D CFTs, these entropy formulas have a very beautiful interpretation of area of black holes in asymptotically ADS3, so these BTZ black holes. And the fact that the entropy is universal for CFTs is due to this very beautiful fact that black hole entropy is completely universal. Right? Black hole entropy, as we learned from Bekenstein and Hawking and others, it doesn't matter about the microscopics of your quantum theory of gravity. The entropy is just given by the area of the black hole, which you can read off from just semi-classical Einstein general relativity. So given that the black hole entropy is universal in ADS3, but also ADS4, ADS5, etc., you might hope that the CFT answer is also universal, at least for holographic theories. Unfortunately, the techniques that we used in 2 dimensions won't work because to compute this trace of the trace of a density of states with this operator state correspondence, you need to compute the path integral on SD minus 1 times S1. And this no longer has modular invariance, right? Modular invariance happens when you exchange this S1 with S1 when D equals 2. And there's a famous theorem of mathematics that D minus 1 equals 1 only has a solution at D equals 2. So, if I do this for a 3D CFT and I compute the partition function on S2 times S1, obviously I can't exchange the S2 and the S1. So the math is different, but the physics is the same. So we might wonder, like, can we make headway through this problem? And the answer will be yes, and that's what I'll try to explain to you in this talk. So in this talk, we'll find that there exists such a universal formula for the density of states, but there are some important differences. By the way, I'm slightly recovering from a cold, so I apologize if I kind of cough in the middle of the talk. So here are a couple of differences between higher D formulas that we will have versus the 2D formulas. First and most importantly, in 2D, this Cardy formula was just determined by a single number, right? So if I give you the single number C, the central charge, that's a single real number, that's some fact of the conformal field theory, then I get the entire entropy up to all orders in perturbation theory of 1 over delta. So one number determines the answer to all orders in perturbation theory. In higher than 2D, that's not going to be the case. There's going to be an infinite series of perturbative corrections. That said, if you're only interested in some finite order in perturbation theory, there's only a finite number of real parameters that we'll need to specify. But there's going to be more than one. So that's the first difference. The second difference, of course, is that there's no analog of Virasoro symmetry in 2D. So we're allowed to count, well, we can always count states, but if we want to organize into primaries, the best we can do is some global primaries as opposed to Virasoro primaries. Okay, so that's of course always true in higher D. And the third thing that's kind of interesting that I'll briefly talk about is that this central charge C has some very nice properties. Like it's some anomaly coefficients in the shows up in the stress tensor OPE with itself, and also it has an RG monotonicity property. The coefficients that will determine the entropy formulas in 2D will not have these RG monotonicity properties. There are like A theorems in 4D and F theorems in 3D, but those aren't what are going to show up in the density of states. So in 2D, kind of the central charge C plays double duty. It's both the entropy and also has some RG monotonicity properties, and that's not going to be the case in higher D. The guy that shows up in the entropy is not necessarily going to be the one that decreases under RG flow. Okay, so that was kind of the intro. Maybe I'll pause briefly if there are any questions before I go on to the technique that we'll use. Okay, so the technique that we're going to be using instead of modular invariance is something called thermal effective field theory. And I should say before I start this, well, this is an old idea, but I learned this was beautifully written up in some papers by Minwala, Bhattacharya, and others from about the early 2010s. And they were looking at this applied to fluid dynamics, hydrodynamics. Well, we'll apply also this to CFTs. The ideas are very simple. The idea is that we want to compute the CFT on some high temperature at some high temperature limit, which is an SD minus 1 times an S1, where the S1 is very small. So we're effectively dimensionally reducing this CFT on a very long, thin cylinder. And generically, this is going to be a gapped, massive quantum field theory in one fewer dimension. The reason this is generically gapped is that there are no parameters we can tune in this problem. This is a CFT, so all length scales are the same. So, the only parameter we have is beta, the length of this circle, which we set to be very small. There's nothing to tune. So generically, we're going to get a massive quantum field theory. More precisely, what I mean is that in this effective D minus 1 dimensional theory, if I compute the 2-point function of two operators separated at points x1 and x2, it's going to fall off exponentially with some correlation length c. And by dimensional analysis, c is going to be proportional to beta, because that's the only length scale in this problem. And we're going to view this gapped theory as a kind of higher dimensional modular dual. So instead of viewing the theory itself as a modular dual, we're going to view this effective D minus 1 dimensional theory as a modular dual, and we're going to write down an effective action of this. And this effective action is going to parameterize the high energy density of states of our CFT. So to be a little bit more concrete, to put a little bit more meat on the bones, we're going to couple our original conformal field theory to a background metric and write the gap theory as a function of these background fields. So first, because this is a circle vibration, we can always write the metric in Klutzig-Klein form. So this is the metric in Klutzig-Klein form as a function of a d-1 dimensional metric, a dilaton, and a d-1 dimensional gauge field. And the partition function of the conformal field theory on this geometry is just captured by the gapped d-1 dimensional theory coupled to these d-1 dimensional background fields. So the CFT as a function of this metric G, this is a background field. It's just the gap theory as a function of the Klutzig-Klein reduction. And the lore of the massive quantum field theory is that this gapped theory is going to be captured by some local effective action of the d-1 dimensional fields. So we're going to say that this gap theory is just e to the minus some thermal effective action, we'd call S thermal, as a function of the metric, the gauge field, and the dilaton. There will be non-perturbative errors if that go as e to the minus 1 over xc. Now, we can't just write down any thermal effective action we want. The symmetry is highly constrained what can possibly show up in the thermal effective action. So what do I mean by this? Well, first of all, I have coordinate invariance of the metric in d dimensions, which translates to, as is usual in Klutzig-Klein theory, d-1 dimensional coordinate invariance and gauge invariance of the Klutzig-Klein gauge field. But also more interestingly, I also have Weyl invariance of the original theory. So the conformal field theory, if I do a Weyl transformation of the metric, it has to be invariant up to a possible Weyl anomaly if the CFT has a Weyl anomaly in even dimensions. And this forces the thermal effective action to be a particular combination of the gauge field and the metric. In particular, it forces this to be this Weyl invariant combination, G hat, which is e to the minus 2 phi times G. Any other combination of the dilaton or the metric won't obey this Weyl rescaling. So this is the most general form of the thermal effective action that we can write down. As a function of the background gauge fields, we integrate over our d-1 dimensional metric, and there are various terms you can write down. We can write down the cosmological constant term, which we call by some convention negative f, and then I can write down an Einstein term, and the Wilson coefficient I call C1. I can write down a Maxwell term, and the Wilson coefficient I call C2, etc., etc. You can kind of keep doing this until the cows come home. And so these Wilson coefficients of this effective theory in d-1 dimensions, f, c1, c2, etc., these will play the role of the central charge of the 2D theory, in the sense that these will be the real parameters that parameterize what the data of the CFT is. So, okay, this is what I said. We'll parameterize universal CFT data, such as density of states, etc., in terms of these parameters f, c1, c2, etc. Let me make a brief aside, and in this language, say why 2D is special. So why is two-dimensional special? So, okay, one answer, which is a perfectly fine answer, is that only in 2 dimensions do you have modular invariance. But in this language of this thermal effective field theory, in 2 dimensions, something also very special happens. In 2 dimensions, if you try to write down an effective theory in 1 dimension, the only term you can write down is f, is the cosmological constant. Right? When you do a Klutzig-Klein reduction of 2 dimensions to 1 dimension, you can't write down an Einstein term or Maxwell term, etc. So in 2 dimensions, this local effective action truncates. The only gauge invariant term you can write down is f. So that's why in 2 dimensions, there's only one number in the central in the high energy density of states, which is this value f. Also in 2 dimensions, this f is the Casimir of the CFT on a circle. So in 2 dimensions, this f is precisely the central charge, and this is what allows us to recover Cardy's formula. Okay, so now that we have this technology, let's try to use this to compute the density of states. We want to know the spin dependence of this density of states. So what we do is we put the theory on a cylinder S1 with radius beta times a sphere SD-1, and we twist the angles on the SD-1 by some beta omega, meaning that as we go around the thermal circle, the sphere gets rotated by some angles beta omega, where this omega is a vector because we allow to rotate in all of the Cartan directions of the sphere. So computing the path integral on this geometry is precisely the same by definition of computing this trace, the partition function of e to the minus beta times the energy plus I beta times omega, these fugacities times the angular momentum. And the claim is that the path integral in this geometry is captured by this local thermal effective action. So now we have a very, very simple algorithm to do. We simply compute this effective action in this geometry right here. This geometry where we put it in the cylinder and then we twist the cylinder slightly as we go around the thermal circle by beta. All we have to do is put the manifold in inclusive-Klein form, plug in our metric, our delta and our gauge field into the thermal effective action, compute as many terms as we want, integrate over dd minus 1 of x with root g, and then now we have our effective action. So this is a very simple calculation that you can give to a graduate student. And when the dust settles, this is the answer you get. So let's stare a little bit at this and unpack it. First, t is just inverse of beta. Okay, so I just want to make this a little bit better. So as a function of the fugacities, that's t and omega, we get these. Here, f, c1, and c2, these are the Wilson coefficients parameterizing the cosmological constant term, the Einstein term, and the Maxwell term that we described earlier. Now, by dimensional analysis, we know exactly the powers of t that each of them come with. The cosmological constant term comes with no derivatives, and so it has to come with t to the d minus 1. This actually is the usual familiar statement of this is just dimensional analysis. This is just, you can compute this just from the entropy of a gas of free particles in d dimensions. Einstein and Maxwell terms, these come with two derivatives, so they come with two fewer powers of temperature. And you can keep going. So suppose you wanted to know the t to the d minus 5 term for this effective action. Then you would need to compute terms like, for example, f to the 4th, or r squared, or r times f squared, or various various contractions of these types of objects.
Nathan, may I ask a question?
Yeah,
what about
please.
log t terms?
Very good question. Very good question. In general, these will not appear. They will only appear. So these log t terms will appear for free theories, and which maybe is what you're referring to. The reason these log t terms appear for free theories is that free theories do not satisfy the assumption that I made at the beginning, which is that when I put this theory on a circle, I want to get a massive gapped quantum field theory. For a free theory, like a free boson, if I put it on a circle, I just get a free boson in one fewer dimension. And so there are gapless modes that I have to take into account, and those will provide the log t terms. In general, for a general CFT, like the 3D Ising model, we don't expect these log t terms to show up in the entropy, precisely because no local thermal effective action can contribute these log t terms in the entropy.
Okay, thanks.
Yeah, it's a very good question. So indeed, actually, as Gabriel said, actually this is very, very constraining because, excuse me, what this tells us is that, well, this t to the d minus 1, this is not very exciting. This is just dimensional analysis. But the functional form of the rest of these terms is completely fixed. They all have to go down in even powers of t. So t to the d minus 1, t to the d minus 3, t to the d minus 5, etc. From this, let me just say, of course, this is the canonical ensemble. We can read off the microcanonical ensemble by just taking an inverse Laplace transform. And then we get the entropy as a function of delta and j. So let me say a couple of, so here's the formula again for the thermal effective action. This is negative log of the partition motion. So this is the free energy, essentially. First of all, let's just make sure we get the right answer in 2 dimensions. So if I plug in d equals 2, this term vanishes. And in fact, all of the higher derivative terms vanish as they must. And we get this expression here. And this is exactly what you get from S transform of the vacuum state at low temperature. This is just a sanity check that we get the right answer in 2 dimensions. Here's another interesting thing, which is you'll notice there's a 1 plus omega squared in the denominator here. So if I plug in omega equals I or negative I get infinity. That's not a coincidence. This is just the unitarity bound of the theory. More precisely, remember what we're computing? We're computing e to the minus beta times this is the dilatation operator, plus I beta omega m. This epsilon naught is a Casimir energy coming from if there's it'll come from some Weyl anomaly terms. So let's imagine I plug in omega equals I. Then what I get is something like e to the minus beta energy plus or minus spin. Right? Let's imagine there's just one angular momentum here. So then if I plug in I, it'll be e to the beta's factored out, and it'll be something e to the minus beta d minus m with some finite shift of the epsilon naught. What this means is that states with E plus or minus j constant going to higher and higher spin get no Boltzmann suppression. So states with the same twist at higher and higher energies have the same Boltzmann suppression. But we know that there are always infinitely many such states, right? These are precisely Regge trajectories. For any CFT, we know that at any fixed twist, at any fixed E minus j, as you go to higher and higher spins, there are always more and more states that have that precise twist and go to higher and higher spins. So there are infinitely many states with that spin with only a finite Boltzmann suppression. So the partition function must diverge. So that's why there's a pole at omega equals I and nowhere before. So it's very nice that kind of this formula knows about this. The third prediction is precisely what Gabriel was saying, which is that this makes very non-trivial predictions for the functional form of the effective action. For example, the power expansion is 1 over t squared, not 1 over t, and the omega dependence is completely fixed. And also these terms like log of t that Gabriel had mentioned, they don't show up for a generic CFT. Now, for very special theories like free theories, where the dimensionally reduced theory is gapless, then of course they could show up, but generically they will not. So as I said, we can take an inverse Laplace transform, and this can give us the density of states, of course. So in 2D, if we do this, this exactly reproduces the Cardy formula that we know and love, and this is the formula you get, and this is just exactly the calculation that Cardy did in 1986. Let me make a very, very brief aside. This is a slight technical comment, but we're expanding in terms of characters instead of exponentials. If we expand in terms of characters instead of exponentials, we can also read off the density of primaries instead of the density of states. That might be more physical because if you know the density of states, like there's some redundancies because like every state comes with a tower of descendants. It's Verma module in 2 dimensions, or it's it's conformal algebra for free. So if we do this for 3D and we expand in characters of the global conformal algebra in 3D, we get this expression for the density of states, for the density of primary operators and for 3D CFTs. And as we see, this first term goes as delta to the 2/3, right? Let's ignore the spin. This is delta to the 2/3. And this is the usual delta to the d minus 1 over d scaling you would get just from dimensional analysis. There are log of delta terms, and these come from doing some one-loop determinant of the saddle point approximation. So there's no log t terms, but log delta is fine. These come from some one-loop expansion. Now here, the C1 and C2, these are again are Einstein and Maxwell terms that show up. And then there's an error term here. I just say that this computation already appeared in a very beautiful paper by Shagulian in 2015 that you guys should, I encourage you to check out if you're interested. And there's a systematic expansion of this in higher derivatives of the effective action. So unlike in 2 dimensions, so in 2 dimensions here, this formula is accurate to all orders in 1 over delta. So well, if you take the log, it's accurate to all orders in 1 over delta. So if you take the entropy and you want to know the corrections, it's actually not this. There's a closed form expression in terms of something called a modular kernel. But there's a known exact expression that's accurate to all orders in perturbation theory, where it's just determined by a single number. And the non-perturbative corrections come from some excited states in the 2D CFT. In 3D or 4D, etc., we don't have such a luxury. Even in the entropy, there are perturbative corrections that have new data. The C1 and C2 you can't derive just from F. You need to compute C1 and C2 yourself. Okay, but if you're only interested in some finite order in 1 over delta, then you only need to go to some finite order in the effective action. And the reason again that this happens in 3D and not in 2D is that in 3D we can write down infinite terms in the effective action, and in 2D we could just write down the cosmological constant. So this tells us the distribution of spins given a fixed delta. If you imagine, fixing delta to be like 1 billion, this tells you spin 0, spin 1, spin 2, spin 3, spin 4, etc., how it falls off, right? Like the entropy is maximized when j is 0, but there's a smooth fall off as a function of j in this formula. And so this tells you like the statistics of the spins. So I like to call this a spin statistics theorem, but apparently that name was taken for something else. That was a joke. Okay. Let me make a brief aside also about some comment that I mentioned earlier about this, which is F counts the entropy at large energies, but this quantity F, remember this F was a cosmological constant in the thermal effective action. This F does not necessarily decrease under RG flow. So in CFT2, it does. In CFT2, this F was precisely the central charge, and it was proven by, well, there's a Zamolodchikov-C theorem proven that the central charge always decreases in 2D. So the Cardy formula, if there's an RG flow from a UV theory to an IR theory, the UV theory at fixed delta always has a larger entropy than the IR theory. Um, um, even though there are F theorems and A theorems in higher D, this F is not that. So actually, maybe I should not have called it F. So there's an F theorem in 3D. This F is completely different. Okay, so this F does not necessarily decrease under RG flow. And I'll give two explicit examples that were computed, that were actually discussed in the 90s. The first one is an example computed by these people in the 90s, and it's an example of a marginal coupling. So if F were to decrease under RG flow, then it's just stay constant under marginal deformation. So this is what happens for C. For example, in the C equals 1 free boson, there's a whole conformal manifolds worth of CFTs related by exactly marginal deformation, but they all have C equals 1. Similarly, in n equals 4 super Young-Mills, this theory famously has exactly marginal operators. So there's a conformal manifold or a moduli space of this theory, which is the usual fundamental domain of SL2Z that we know and love. It was computed in the 90s by these people that as you go from the free point to the holographic point, so going from zero Chuft coupling to very large Chuft coupling, this factor F changes by a factor of 3/4. I think it decreases by a factor of 3/4. So it doesn't stay constant, it decreases by a factor of 3/4. And this is this famous like 3/4 mismatch in entropy. If you just take free n equals 4 super Young-Mills, so just take some number of however many scalars, fermions, scalar spinors and vectors, and just compute the entropy and compare it to the entropy of black holes, you're going to be off by a factor of 3/4 in F. Actually, all of the Wilson coefficients you'll be off by various factors, and it's kind of interesting to and there's a lot of work people, they show that, in perturbation theory in both directions, they go closer to each other, etc. But the point is F doesn't stay constant. The second example is by Sachdev in the 90s. It's even a little bit more drastic, I think. This has showed that the ON model at large n, there's an RG flow where it flows to some n-1 free scalar fields. And here F increases under RG flow. It increases by a factor of 5/4 in the large n limit. So this F is not constant under RG flow. Sorry. This F is not decreased. It's not monotonic under RG flow. Okay, that was just kind of an aside, but I just wanted to emphasize this because it's important to emphasize the differences between what happens in higher D versus what happens in 2D. So let me ask also what the regime of validity of our entropy formula is here. So here I've computed the entropy as a function of delta and J, and I've done this expansion. But there's some terms that might look a little bit funny. Like this one, if J is 0, this goes as 1 over delta squared. So, but this error goes as 1 over delta to the minus 1/3. So this might be smaller than the error, and so you might be confused. Like similarly though, if J goes all the way to delta, this term looks like it's blowing up. So you might wonder what the regime of validity of this entropy formula is, which I kind of swept under the rug earlier. And that's very easy to answer this question. To get this, we took an inverse Laplace transform and we did a saddle point approximation. And the whole point of this thermal effective action is it's only valid at high temperature. We're doing an expansion in 1 over temperature. So when we did this inverse Laplace transform and evaluated the saddle, we need the saddle to be at large temperature. Like if the saddle is at small temperature, we just don't trust our answer. So you can just compute the saddle and see what that means. And here's the final answer. So for D equals 2, this is the usual Cardy formula. And the answer there is that the dimension minus the spin must be very large compared to the central charge. Okay. Now in higher than 2 dimensions, the dimension minus the spin, I should probably not put the absolute value signs here because the spin is always positive if we do representations. But the dimension minus the spin must be, instead of much larger than the central charge or much larger than F, the formula actually changes. It goes as square root of F times delta. As an aside, here I just turned on one fugacity. If you turn on multiple, this squared will change. But let's just turn on one fugacity for now. Okay, so this formula is valid when delta minus J is much bigger than square root of F times delta. And now you can see actually this makes this term safe. This term does not blow up. This term is always smaller than this term over here, because even if we saturate this and delta minus j scales as square root of delta, this will be smaller than this term over here. So it's interesting that our formula is not valid at the unitarity bound. The unitarity bound of the CFT is always roughly delta minus j is a constant. So it's always roughly delta equals j. And when delta equals j, we don't obey this equation. So our formula is not valid at the unitarity bound. So we don't have a universal expression for the entropy at the unitarity bound. I'm going to comment a little bit more about this when I talk about holographic theories, because actually this formula has a very nice interpretation in terms of black holes in ADS Kerr black holes. But maybe I'll put this aside for now. So let me pause here if there are questions. I'm going to now go through some examples, but maybe I'll take some questions. Excuse me. Okay. Okay, so let's go through some examples to get some intuition of this for some various d bigger than 2 theories. The first example I'll do is free theories. Here we can compute the partition function just exactly and verify it takes the functional form we predict. As was pointed out by Gabriel, we need to be careful with these free theories because they have gapless modes. So there is some caveat, but well, we can discuss it afterwards. You can actually just compute the action of these gapless modes, and they'll give the log t terms that was mentioned earlier. Or you can put these theories with some different boundary conditions that get rid of the gapless modes. And the other example I'll compute is some holographic theories, where we can approximate this partition function by computing the area of some Kerr ADS black hole, and we can verify it takes this proper functional form. So as I said, free theories are subtle. There's a gapless sector because there's a free theory in d-1 dimensions, but you can compute this and you can take care of it. And for free theory, free scalar and free fermion, you can just explicitly read out these expressions, and you get these values for these Wilson coefficients for a free scalar or a free fermion. And the functional form takes exactly as we predict, and you can just compute this as a function of d. So okay, these free theories, fine, they're not very exciting. More interesting are holographic theories. And this we can read off the leading term in the Wilson coefficients using black hole thermodynamics. So just by looking at the area of an ADS Kerr black hole, we can read off the expansion in 1 over t. And this was done by some, well, no, this was done, in the 70s, really. And you can read off the exact expression of this entropy. I should not say it's exact, actually. Of course, there will be corrections from stringy corrections and quantum corrections, and those could be theory dependent. Certainly, we can't read those off from Einstein gravity, so we'll leave those aside. We'll just say the leading order semi-classical answer. So to leading order in 1 over g Newton, we have this expression for f, c1, and c2. These are the leading order expressions for these Wilson coefficients. They all go as LADS to the d-1 over g Newton. This is some dimensionless quantity. Here, d is the CFT dimension, not the gravity dimension, and g Newton is the d plus 1 dimensional Newton constant. And of course, all of these could in principle have corrections that we don't necessarily know how to compute. By the way, this term right here that I'm highlighting, this f, this is what differs from a factor of 3/4 when d equals 4 to free n equals 4 to Briagno. So this was what was computed by like Gubser, Klemenov, P, Ted Zeitlin, and others. Okay, any questions on this? By the way, you can think of this as, it's kind of interesting. You can think of this as a higher dimensional analog of the Brown-Fano formula. I don't mean this in terms of so remember the Brown-Fano formula related the central charge C for 2D CFT to LADS over G Newton or LADS over L Planck to in ADS3. So the formula is roughly C equals LADS over G Newton times that order 1 factor, which I don't remember. And this is kind of a higher dimensional analog of Brown-Fano. I don't mean this in terms of any asymptotic algebra and infinity, anything like that. But what I mean is that these Wilson coefficients are related to LADS to the d-1 over G Newton. And this is precisely what Brown-Hano is telling you. They're telling you what the thermal effective action degrees, Wilson coefficients are related to the dual CFT cosmological constant. And that's exactly what this is saying. The dual CFT cosmological constant is related to these Wilson coefficients by these precise order 1 numbers that you can't fix. And this is very interesting because it's like, now it's saying that these holographic theories have an infinite number of constraints that they must obey. So unlike in ADS3 CFT2, in ADS3 CFT2, this Brown-Hano is almost guaranteed because of the Zalmoja constancy theorem. Once you fix the central charge, then the central charge matches for the dual CFT and the gravity theory. But here, this is no longer the case. Like for n equals 4 super Young-Mills, this F doesn't match at the free point. So as you perturb by marginal deformation, only at the strongly coupled point, the larger Tuff limit, does this F match. And same with the C1 and C2. So somehow there are like an infinite number of constraints that these higher dimensional holographic theories must obey. And it would be very interesting if we could prove that from CFT first principles. Okay, let me now mention again, let me go back to this point right here of the regime of validity of our entropy. And I'm now going to review some fact that was a pure GR fact that was discovered not so long ago, actually, 2004, as far as I'm aware, which is that current black holes in ADS for d bigger than 3 suffer from an instability. This is called a super-radiant instability. And it was shown that these black holes are only stable. Basically, if the black holes spin too quickly, if they're too close to the unitarity bound, they're not stable. Or more precisely, the most precise statement I should say is that there's another solution which dominates the canonical ensemble. There was a very recent interesting, well, there were some interesting recent papers by various people, Minwala, Sok Kim, and others, that propose an endpoint of this instability. I'm not going to discuss that. I'll just say where their black holes are stable. Their black holes are stable if the energy of the black hole minus the spin in appropriate units is bigger than some order 1 number times the square root of the energy over square root of g Newton, and the LADSs make up the units. And this is very, very similar to the condition we found for the CFT entropy to be valid. So the CFT entropy was valid if the energy of the state minus the spin was much bigger than square root of F times delta. And if you translate these to CFT to the gravity values, this is exactly this formula. We replace this 1 greater than sign with 2 greater than signs. Let me make an analogy to what happens in ADS3 CFT2. So in 2D, there's some famous extension of Cardy's formula for holographic theories using modular invariance. This was by Hartman, Keller, and Stoica about a decade ago. And what Hartman, Keller, and Stoica argued was the following. They said, the Cardy formula is valid when the twist is much bigger than the central charge. But they argued, using modular invariance, that if some sparseness condition were met, then you can get rid of these 2 greater than signs and just make a 1 greater than sign, basically. They say if the twist is bigger than, there's an order 1 number times C is enough. I think it was C over 6, but I'm not going to worry about the order 1 numbers in this talk today. And this is also precisely where black holes are stable in ADS3, where BTZ black holes dominate the canonical ensemble. So it's very, very reasonable to conjecture that some similar formula will exist, some similar extension will exist in higher dimensions. So our formula is valid when the twist is much bigger than square root of F times delta, but it's very reasonable to conjecture that if there's some holographic condition, maybe sparseness, maybe chaos, I don't know, maybe gap in the higher spin sector, then we can extend our entropy formula to just scaling parametrically like square root of F delta with an order 1 number to match where the black holes are stable. I find this very suggestive because on a technical level, the calculation needed to get this scaling for the CFT and this scaling for the black holes is completely different, but they give the same functional form. So I think that's quite suggestive, although it could just be a coincidence, but I don't think it's a coincidence. Okay, so with all of that, I'll finally now talk about what we did in our recent paper. So this is all kind of review, but in the final 15 minutes, I'll just introduce to you what I promised you at the beginning of the talk, which is what happens for large chemical potential. So remember at the beginning of the talk, I said, oh, what we're really interested is what happens when this omega is an order 1 is no longer an order 1 number, but very large, like pi over beta. And this will now compute the trace of the partition function with a -1 to the j inserted. right? And in 2 dimensions, we did this using a more complicated modular transform. But in higher dimensions, obviously, we don't have SL2Z. And so in higher dimensions, how can we get access to this spin-refined information, like even states minus odd states, or spin discrimination mod 3 or mod 4, mod 5, whatever. So far, we've been computing this partition function for a small beta in order 1 chemical potential. But now I'd like to compute it when omega is large. So beta omega is order 1. So for example, this would include trace minus 1 to the j, e to the minus beta h plus I omega j. Any questions on what we discussed, or where I want to discuss what I want to discuss now for the last 15 minutes? Okay, so in 2 dimensions, of course, we computed this like we did in the beginning of the talk. In 2 dimensions, this at high temperature, so small beta, we can compute this using a more complicated SL2Z modular transform. If you use this more complicated modular transform, you'll map this to the vacuum state again, and the vacuum state has a universal Casimir energy, and you'll be able to answer this question. But so again, always when I write this, I want to take beta small and omega to be order 1. But now there's a large minus 1 to the j. And if you do this modular transform, you can this you could give to a Mathematica or to a grad student, whatever. You get this expression, and you get that the free energy is down by this factor of 4. So if you remember, the Cardy formula didn't have this factor of 4 in the denominator. Here you'll have this factor of 4 here. And in fact, more generally, if you put in e to the 2 pi I p over q, where p and q are coprime, you'll be down by a factor of q squared. Okay. So what I'm going to do now in the rest of this talk is I'm going to now rederive this, not using modular invariance, but using thermal effective field theory, and this will tell us how this generalizes to higher dimensions. So let's suppose I wanted to compute this partition function in higher dimensions. So for simplicity, I'm just going to put one fugacity and 1 spin, but it generalizes to multiple spins as long as they all commute, and I'll describe what that is afterwards. So suppose I want to compute this partition function, trace minus 1 to the j, e to the minus beta h plus I omega j. That's the same as doing this path integral with this minus 1 to the j insertion, where this minus 1 to the j performs a pi rotation of the sphere. Okay. So pictorially, what that's saying is we compute the path integral where we identify no longer now the bottom with the top, but with this pi rotation. And what this pi rotation does is it takes the left SD minus 1 at here at SS1 and maps it over here, and this maps over here. Does that make sense? So this is like the definition of minus 1 to the j in some sense. So if we compute the path integral now in this funny geometry as a function of beta, that will give us this trace. And now the point of a path integral is an integral, so we can we can do cutting and pasting of our geometry. So what I'm going to do is I'm going to cut and paste this geometry and place one half of this geometry on top of the other half. So I'm going to cut this circle, this ST minus 1, this sphere in half, and place one on top of this geometry. So I'm now going to compute this geometry on this geometry right here. So this is exactly the same as this geometry. So all I did was I put one on top of the other. So now the fact that this left part is identified with this right part now means that this is identified with this. This guy being identified with itself says that this is identified with this. And this being identified with this says that this bottom is identified with this top. And now the length of this thermal circle is 2 beta. And now instead of the spatial circle being in SD minus 1, it's now this quotient space SD minus 1 mod Z2. Okay, so any questions on what we did with this path integral? And now here's the key part, which is we're going to use thermal effective field theory, and we're going to assume that 2 beta is much smaller than 1. And now we're going to get a gap theory on SD minus 1 mod Z2. And the point is, we're now going to get the same gap theory, because what's going to happen? The only difference is now this S1 with length 2 beta is now non-trivially fibered over the SD minus 1 mod Z2. There's a non-trivial circle vibration, because as you go around, there's this funny identification. When does this non-trivial vibration matter? This only matters for topological terms. For local gauge invariant quantities, they don't know the global geometry. They don't know the non-trivial vibration. So for terms like the Maxwell term or the Einstein term, whatever, they're not going to realize that this geometry is non-trivially fibered. So we'll get the exact same action. There is one exception of when this theory will realize that the theory is non-trivially fibered, which is that if there's a Chern-Simons term in our thermal effective action, which I actually haven't discussed, and that happens when when the original CFT has a gravitational anomaly. So for example, in a 2D theory with C left not equal to C right, or a 4D theory with a gravitational anomaly. If that happens, there will be a Chern-Simons term that will be different for this geometry, and I can discuss this afterwards if you're interested. So if you're interested in that, we can chat about it. But for now, let's assume that our CFT doesn't have a gravitational anomaly, and so then no terms in the local thermal effective action will notice this non-trivial vibration. So what happens then? So there are two things that happen. First, the temperature goes down by a factor of 2, right? Because beta goes to 2 beta. And second, this volume of SD minus 1 goes down by a factor of 2 as well. Because now instead of SD minus 1, it's SD minus 1 mod Z2. So this goes down by a factor of 2, which gives us a factor of 1 over 2 to the D minus 1. And this goes down by a factor of 1 over 2, just there. So overall, we get a factor of 1 over 2 to the D in this free energy. Any questions how I derived this 1 over 2 to the D? So it was a little bit fast, so let me go through the logic one more time. So the logic is we want to compute this partition function with a minus 1 to the j. That's the same as computing the path integral on the cylinder, SD minus 1 times S1, with this funny identification. Because the point of the minus 1 to the j is it rotates the sphere by pi degrees. Now we're going to do some cutting and gluing of this geometry. We're going to stack this left part on top of this right part. If we stack this left half on top of this right half, the first thing that happens is this SD minus 1 becomes an SD minus 1 mod Z2, where this Z2 action is a rotation of the sphere by by 180 degrees. The identification now, because this left side is identified with this right side, but now I stack them, that means that this is identified with this, and this is identified with this, and again, the bottom is identified with the top. And now we're going to look at the effective thermal action we get on this funny geometry. The circle is now non-trivially fibered, but for any local gauge invariant quantities, they won't notice the non-trivial vibration. So the Wilson coefficients of this new thermal effective action are exactly the same. So then all that happens is this temperature goes down by a factor of 2, which gives a 2 to the D minus 1, and this volume goes down by a factor of 2, which gives a 2 to the D. So the leading order term in the thermal effective action goes down by a factor of 2 to the D. So if D equals 2, this reproduces the factor of 1/4. Yeah, so down by factor is what I said, down by factor of 2 to the D, 1 over 2 to the D minus 1, and 1 over from the T to the D minus 1, and 1/2 from the SD minus 1 mod Z2. This 2 to the D reproduces the factor of 1/4 when D equals 2. By the way, the higher derivative terms will be down by other factors. So for example, the Einstein term will still have this volume and T to the D minus 3. So that will be down by 1 over 2 to the D minus 2. Because you get a 1 over 2 to the D minus 3 from T to the D minus 3, and again a 1 over 2 from the volume. However, there are two other things I need to keep in mind. One is, as I said, if there's a gravitational anomaly, there are Chern-Simons terms that will be different. The second thing is that there's this SD I wrote here. What is this SD? Well, this SD minus 1 mod Z2, this is a singular geometry. If D is bigger than 2, there are fixed points of this geometry. So, okay, for S1 mod Z2, there are no fixed points, because S1 mod Z2, when I rotate this S1, remember, this Z2 is a pi rotation. So if I rotate this S1, then there are no fixed points. But let's say D equals 3. So I take an S2 mod Z2. Then the north and the south pole are fixed points of this rotation. So in principle, there could be a defect action that lives on this fixed point. So in general, there will be a new defect action that you can write down, and there will be a new effective theory you have to write down localized solely on these defects. So in general, these defects will be higher codimensioned, which means they'll be lower in the powers of the temperature, but they'll still show up in perturbation theory. So this S defect, for example, it might show up at the same as the Einstein and Maxwell term in the perturbation theory. These will have new Wilson coefficients that you can't compute from first principles, just from the CFT. So there will also be a local defect action living at a fixed locus of the Z2. And this will be some perturbative correction in the 1 over T expansion, but it won't compete with this leading term. This leading term is still the most important because the defect is at some higher codimension. So I did this here with a phase of minus 1 to the j. In general, you can also have a phase of e to the 2 pi I p over q. And then if then you have to do a more complicated cutting and gluing. and you'll get a factor of q to the d for this term right here. There are a couple other subtle points that maybe I won't go into in the talk, but if you're interested, you can ask me afterwards. I assume the theory is bosonic, but for fermionic theories, it's slightly different. It's not so difficult. You can still deal with it, but for fermionic theories, it's different. And why is it different for fermionic theories? For fermionic theories, you need to specify not just the manifold, but you also need to specify a spin structure on your manifold. And on SD minus 1 times S1, well, the only one with non-trivial homotopy is this S1. So you need to tell me what the periodicity of the fermions is around this S1, if they're periodic or if they're antiperiodic. And what that corresponds to is an insertion of the minus 1 to the f or without a minus 1 to the f into your trace, right? And but you see, let's imagine I started without a minus 1 to the f. So let's imagine the fermions are antiperiodic along this S1. But here I did this cutting and stacking, and it could be the case that after the stacking, I go around this thermal cycle an even number of times, and the periodicity changes. So it could be the case for fermionic theories that my new effective action now has a minus 1 to the f inserted. So for fermionic theories, there are two effective actions you need to write down. One with two sets of Wilson coefficients you need to write down. One with a minus 1 to the f insertion, and one without a minus 1 to the f insertion. And depending on this phase, either the 2 pi I p over q, it depends on if p plus q is even or odd. So it depends on the parity of p plus q. Then you'll either reduce to the thermal effective action with or without the minus 1 to the f. By the way, this is exactly what happens in 2 dimensions. And in 2 dimensions, this is the difference of the growth is precisely the ground state energy of the Ramon sector. And so the difference of these Wilson coefficients, you can think of as a higher dimensional analog of the Ramon sector ground state energy, in the sense that it tells you the difference of the density of states with and without this minus 1 to the f. So I can say more about this if this afterwards if people are interested. But it's not that the story is any different for fermionic theories, it's just slightly more subtle, but the story still goes through. I think I'm just about out of time. So let me just summarize and then I'll take questions. So in this talk, I described a technique called thermal effective action that systematically studies CFT data at large dimension. This is kind of a cheat. We don't have modular invariance, but we do have effective field theory, and this allows us to reproduce a lot of the results of modular invariance just using the principles of EFT. And this encodes the spectrum of local CFT operators as a function of their dimension and spin at large dimension, which we checked in this talk against free and holographic theories. And we obtained large chemical potential formulas, which are the analog of other elements of SL2Z, not the S transform, but other elements of SL2Z. And using similar techniques of cutting and gluing, we were able to reproduce some of these formulas for higher dimensions. And these are analogs of inserting a minus 1 to the j into the partition function, which we were able to get for higher dimensional CFTs. So I'll just conclude there, and I'll take any questions. So thank you very much for your time.
Thanks very much.